from University of Colorado in Boulder, where she's doing her postdoc. She started her postdoc actually at the University of South Carolina, but she ended up moving to Boulder because an advisor actually moved. She has a bachelor's degree in material science from Hefei University of Technology in China, and a master's also in material science from the Institute of Metal Research, China's Academy of Sciences in China, and a PhD in mechanical engineering from University of Pittsburgh. So I'll have Dr. Yana talk about her research.
Thank you
and welcome to CSU.
Good afternoon, everyone. It's really a great pleasure to be giving this opportunity to present my work here. My talk today is the first principle-based multi-scale, multi-physics approach for the integrated computational materials engineering. Is my voice loud enough for everybody to hear me? Okay. Yeah. So first, I'd like to give a snapshot on what I have been mainly worked on. I have some experience in using the combined experimental approach, including the electron microscopy, the surface analysis, and the electrochemical techniques to characterize the anti-thermal property of a kind of high metal steel. And starting from my PhD, I started to use the computational techniques to characterize the various materials, including metals, carbon-related materials, and the polymers, to investigate the structure property relation. I also contribute to the atomic continuum bridging method to develop a multi-scale framework. And recently, I was working on the process design using the computational techniques, mainly to predict the microstructure evolution in the additive manufacturing process. So now a growing tendency in the process and material design is to further combine with the product design, as indicated by the integrated computational materials engineering and the material genome initiative. In the traditional way, the process design, material, and product design are somehow disconnected, while the material supplier would have information on the process-dependent structure, and a different community or team might be interested in the structure-dependent property, while in the product design stage, the material engineering will choose from the existing pool of materials based on the required performance. Well, in the new ICME, Integrated Computational Materials Engineering Paradigm, it's hopefully that we could link the process, structure, property, and performance all together by combining the manufacturing design as well as the concurrent materials and product design in a seamless computational environment. Also, this goal-oriented ICME approach would enable us to choose from the materials parameters, material composition, and the processing parameters if this inverse design can be enabled. To realize this ICME framework, it's very important to build computational multi-scale multi-physics framework, because for both the materials and process, they could involve multiple physical phenomena at different length scales. So with this multi-scale framework, we could investigate the structure as well as the property at different length scales and further bridge them together for product performance. Also, this first principles-based computational framework would need no input from the empirical physics parameters or the assumptions, so can bring some new perspectives in the materials and process design. So the first principle-based simulations are called ab initio simulation, studied directly from the essential laws of physics. Good example, this would be using the Schrodinger equation to predict the electronic structure of atoms and materials. But this is very computational costly, so to reduce the computational cost while maintaining certain accuracy, molecular dynamic simulation is a very good option, in which the interatomic potential is written in terms of the atom position. So we won't be able to see the electronic structures in the RD simulation. And this it has been widely used for studying nanowires, nanotubes, and biomoleculars. So next I will show how we use the MD simulation to characterize the mechanical properties of polymer nanocomposites consists of polymer or copolymer matrix, as well as nanoparticle or nanofillers dispersed into the polymer matrix. Some commonly used matrix polymer and nanofillers are listed here, and has wide applications from the automobile, aircraft to electronic devices, as well as some biomedical applications. In most of these applications, the mechanical properties is very important. So this PNC we choose has a polymer matrix based on the polyethylene, and we use a coarse grain model, which is built upon this full atomistic model. So we can see that one carbon atom and two hydrogen atoms are grouped into a superatom, and their interactions are described using this bond stretching, bending, and torsion, as well as non-bonding interaction. We also have the coarse grain model for this nanoparticle, which by placing the 80 superatoms on the surface of the nanoparticle. The nanoparticle, this gives a materials model that we build by combining this nanoparticle and the polymers. And this nanoparticle can interact with the polymer using these non-bonding interactions, epsilon and p. And these interaction strengths can be changed, representing different interactions between the nanoparticle and polymers. Also, we have the nanoparticle interaction, as well as polymer-polymer interaction. This gives some simulation details on how we construct the system and equilibrate it, as well as gradually cool it down to lower temperature. And finally, we apply some uniaxial loading, both the tensile loading and compressive loading at 200 Kelvin until a true strain of 100% is reached. The microscopic parameters we are interested in are the non-bonding interaction strength between the nanoparticle and polymer, represented by epsilon and p, and also the nanoparticle volume fraction up to 21%. So we are going to see how these microscopic parameters are going to influence the mechanical properties. First, let us look at some snapshot of the polymer nanocomposites under tension at a strain of 50%. So we have the polymer with no nanoparticle addition has demonstrated uniform deformation at this strain level. And when we add the nanoparticle or low the nanoparticle polymer interaction strength, we can find there's nanoparticle agglomeration, which could potentially weaken the materials. And here we further increase the nanoparticle polymer interaction strength, and there's a localized deformation happen at this strain level. When we further increase it at very high empty volume fraction, we find the uniform deformation is resumed again. Now here I show some true stress strain curves of the polymer nanocomposites. So first let us look at this black line, which is the polymer response without any nanoparticle loading. So it shows the typical response of polymeric system, shows the elastic region of strain softening as well as strain hardening. We can extract some important mechanical parameters from this curve, such as the elastic modulus, the yield stress, as well as the strain hardening modulus. And we have compared these results with the experimental available data as well as previous simulation results, and shows pretty good agreement. And the four different plots represent the different nanoparticle polymer interaction strengths from very low and to very high. And the different curve represent different nanoparticle loading volume fraction. So we find that when the nanoparticle polymer interaction strength is smaller or equivalent to the polymer-polymer interaction strength, the NP addition is not reinforcing the polymer nanocomposites. We can see those lines are lying under this pure polymer line. This could be combining with the snapshots we see at the previous slide, things caused by the polymer agglomeration that could weaken the material. And here, when we further increase the nanoparticle polymer interaction strength, we first find the reinforcement in the compressive domain. But in the tensile domain, we only find it in the elastic part. But in the plastic part, the original strain hardening is replaced by strain softening. Also combined with the snapshot, we could imagine that this localized deformation could possibly contribute to the strain softening happened here. And when we further increase the nanoparticle polymer interaction strength, we find the reinforcement again in the tensile loading domain in the plastic region. Especially when we have a very high the nanoparticle volume fraction and this original strain hardening is resumed again. So we can also see from the snapshots that the uniform deformation is resumed again instead of this localized deformation or nanoparticle agglomeration. We further did some study on the dynamic response to the shockwave loading, and this project is of interest to our collaborator at the Naval Research Laboratory for polymer usage, like a polymer film for shock mitigation. So the general system is similar to the one we previously did, but we did some simple modification to the nanoparticle structure. We didn't put superatoms on the surface, rather we just used one sphere to represent the nanoparticles. So to initiate shock wave, we used this projectile wall geometry, just placing a wall at the x equal to 0, having a reflective wall boundary condition. So when this polymer bar is giving a velocity at ut and hit this wall, you will get a reverse of the velocity. So we consider two cases of the chain length, 10 and 500. We also consider the uniform nanoparticle loading up to 31%. Because from the previous studies, we find we need a strong nanoparticle polymer interaction strength to reinforce the nanoparticle, to reinforce the PNCs. So here we choose a pretty strong nanoparticle polymer interaction strength. So besides this uniform nanoparticle loading, we also design some kind of microstructure by alternatively aligning this nanoparticle containing part and the nanoparticle free part. So this nanoparticle containing part can be regarded as the soft region, and this nanoparticle free part can be regarded as the soft region. So in total, we investigate 8 kind of microstructure. And here gives position time diagram of the polymers under shock. So we see that T1 and T2, with time, we could find this shocked region is linearly increasing with time, while this unshocked region is decreasing, which shows the steady propagation of the shock wave. Along the time, we also record the velocity, pressure, and density. Here give a snapshot. We can easily identify the shock front indicated by those arrows that separate by the unshocked and shocked part. This is the jump in the profile. And this different color represent the different nanoparticle loading fraction. We can find that with increasing the nanoparticle volume fraction, there's increasing of the shock wave propagation speed. We are also interested in the shock Huygenius. So we computed the shock velocity based on this expression according to the balance of mass. And this, we also compare these our simulation results with these experimental results, which is indicated by the dashed line, and found really good agreement for the pure polymer without any nanoparticle addition. We found that with increasing the nanoparticle loading volume fraction and increasing the chain length, and there's also an increase in the shock wave propagation speed, which is understandable because the shock impedance is increasing increased by the nanoparticle and also the chain length. So besides the uniform nanoparticle loading, we also interested in the influence of layer structure. So we compute the scalar slip of all the superatoms and plotted here, which is an indication of the microstructure, microscopic deformation. We can see the shock front very easily by the contrast in color, where the red color is very close to 0 scalar slip, and this blue color is very close to the maximum scalar slip. And we also compare two different chain length systems, also combine with this figure, which is an average over the YZ plane of this figure, shows a variation of the scalar slip along the x direction. We find this kind of layer structure promotes the formation in the soft part, which could absorb the energy. And also, when we have shorter chain length, and this deformation in the soft part is further enhanced. We also compare two different layer thickness of the nanoparticle containing region, and find that increased layer thickness will further promote deformation in the soft part, as seen by the contrast in color here. So here I'm going to talk about another one. It's a cross-linked epoxy resin in the autoclave cure process, and this project is currently funded by the Navy Air STTR Phase 1 program. We just finished the Phase 1 review and actively preparing for the Phase 2 proposal. So the objective of this project is to predict the manufacturing defects happening in the autoclave process for the composite materials. So the thermoset epoxy resin is commonly used for the polymer matrix for composite materials in DOD usage. And this epoxy resin is mixed with the fiber to make the cool pack during the autoclave process, and the temperature as well as the pressure would be increased. And the curing process could happen, which would affect the thermomechanical properties of the epoxy resin. So we need to capture or predict those thermomechanical changes during this curing process with pressure, time, as well as curing degree, in order to predict the manufacturing defects, which could lead to unexpected materials behaviors. So the epoxy resin system we choose is composed of DGBA and IPD, which is commonly used industrial epoxy resin system. So we need to create a cross-linking degree varies from 0% to 92%, which is very close to the experimental value. So we have an in-house code to create bond between the epoxy ring and also the imide. So to create some bond between these the two reactive sites in order to create the different cross-linking degrees. So we conducted MD simulation to characterize those mechanical properties to see their change with the time and cross-linking degree. Because their dependence on the pressure is relatively low, so we didn't consider the pressure as an influencing factor. So we first do some cooling simulation that gradually bring down the temperature of the whole system and measure the density. And the curve is given here. So from this plot, we could get many information, such as the glass transition temperature, the thermal expansion coefficient, as well as the volume shrinkage. So we first see how to get the glassy transition temperature. We do linear fitting to this curve, and we will see a transition in the slope of this fitting line. And this intersection is the TG, giving indication of this glass transition temperature. Here we calculated for the virus different cross-linking system. And also from the slope of this fitting line, we can get the thermal expansion coefficient. For the rubber state and the glassy state, their value for the different cross-link system are given here. And also we can have the specific volume and virus temperature and their change with the cross-linking degree, which could be fitted using this model and further used for the continuum simulation. We further did some uniaxial loading simulation, which is similar to the one I previously showed, and extract some important mechanical properties such as the elastic modulus for both compression and tension and virus temperature, as well as the yield stress. And then for the viscosity, we obtained from the homogeneous shear simulation. This gives the model, and also called Coetta model, and the viscosity at various temperature for different cross-linking degree are obtained here. So the results I showed are mainly to use MD simulation or coarse-grained MD simulation to categorize the material's properties, which could provide information to this representative volume, or which could be further used for the coarser scale simulation. But in the semi-concurrent multi-scale simulation or concurrent simulation, we also sometimes need to exchange information between the fine scale and the coarser scale in the bridging domain. So later on, I will talk about my work on this part. So even though the MD simulation is a good option when we want to categorize the material's properties, and it also have lower computational costs compared with those ab initio simulations, but overall it's still very computational costly compared with this finite element analysis at coarser element level. So especially when we want to investigate the influence of materials parameters as well as the external stimuli on the response of the overall system, which need us to do the simulation, change the parameter many times. So in this case, the model order reduction is a good option because it can bring down the number of degree of freedom of the original full atomistic system greatly. So, but the problem in the conventional model order reduction is that we need to do the online projection between the reduced order coordinates and these physical coordinates very frequently, which is very computational costly. So because we only build the reduced order model for the displacement field. So in our approach, we try to build a reduced order model of the phase field besides the displacement field using this HPPOD, Popper orthogonal composition and moving least squared algorithm. So that will save the time to project between the reduced order spaces and this physical space at online stage, which further saves the computational cost. So combined with this atomistic characterization and these reduced order model approaches, we could altogether provide information for this micro-continuum simulation. Here, for example, using the results I characterized for the epoxy resin system and then put into reduced order model, and we could provide information to the continuum model consisting of the flow compaction, fluid kinetic temperature evolution, and the residual stress for the prediction of the resin bridge starvation and the curing degree, and also the warpage. So now I'm going to talk about a little bit my theoretical work on the atomistic continuum bridging method, which could be used in the concurrent modeling. Can also be used if you have a simulation result at the nanoscale, you want to use continuum description on it. So we typically want to consider a case for the inhomogeneous system away from equilibrium. So with the information at the nanoscale, the atomic velocity, position, and interatomic potential, we want to have continuum description based on the stress, heat flux, and temperature. So our development is based on the Hardy theorem because it has some advantages compared to the other theorem, but it has a limitation that was developed for the paired potential system. It means that total energy of the system can be written as a form as a sum over pairs of atoms. So based on the Hardy's theorem, the stress and heat flux at the left-hand side can be written in the atomic quantities at the right-hand side, where all the needed atomic quantities are listed in the table here. We can easily access them from the MD simulations. And the key in linking this atomicity to continuum is this localization function, which gives different weight to those atoms that contribute to contribution in this spatial point X at continuum region. So, but I talk about this limitation in the Hardy theorem is that it was developed for pair potential system, where this Fij is very straightforward. It means the force on atom I from atom J. But for multi-body potential system, this is very problematic and not straightforward. So we propose that if we define Fij based on this expression, and the assumption in the derivation of the Hardy theorem can be satisfied. So for n-body potential system, this Fij doesn't only have contribution from this pair-body term, also from the three-body up to n-body term. And more specifically for polymeric system, we have bond stretching and non-bonding term, which are two-body terms. And these bending and torsional terms are three- and four-body terms. So in total, we have contribution from stretch, non-bonding, bending potential, and also the torsional term for the Fij. Here shows an example how I apply those expressions for a system. I only showed how I derive for the stress. In the same way, the heat flux and temperature can also be derived. So I apply it on the epoxy resin on the Poisson flow, represent the epoxy resin flow between two fiber surface in a nanochannel. So for both uncross-linked system and cross-linked system. So the first two are stress and the heat flux and temperature. And there's a lot of fluctuation because the high temperature adopted, but we still can capture some tendency where in the upper panel, the color is dominated by blue, and the lower dominated by yellow, which shows opposite sign of this shear stress. Well, from this velocity profile, we can see there should be opposite sign of the shear stress, which shows it gives the reasonable results. We also capture some hotspots caused by the non-stable boundary conditions. Well, in terms of temperature field, we find there's a non-cross-linked system create more elevated temperature compared with the cross-linked system. So of course, all these simulation results and computational prediction needs to be combined with experiments in the way that we need to collect experimental data and through data processing, realize our computational reconstruction, which will form a hypothesis to our theoretical model, and also to validate our simulation results with these experimental results. Recently, we got interested in using the phase modeling to predict the microstructure evolution in the additive manufacturing process. The AM, or called 3D printing, is very familiar to both of us as rapid prototyping techniques, and they can fabricate complex net-shaped products through the successive addition of materials. And here it gives some types of 3D printing, and I also show a figure for the 3D metal printing in the selective laser melting, which our modeling is mainly based on at this point. So in this selective laser melting of metal, the thin slice of metal powder will be selectively melted by the high power laser beam to make the 2D slice of the part geometry. And this whole process will happen in a chamber containing the tightly controlled atmosphere of inert gas. And there are also some AM products, including jet engines. Also, there's an increasing usage in the biomedical area, such as the 3D scaffold for tissue engineering, the implant for bone replacement, as well as the heart valves. So this is the experimental results we got from our collaborator at the Naval Research Laboratory, and we find there's a drastic change of the microstructure compared with the conventional process, the 316L stainless steel, and is featured by the highly non-uniform of the grain size as well as the irregular grains. And there's another published work on similar. We can find there's a highly distribution of the grain size. So that could be attributed to the additive manufacturer featured very high cooling rate, also directional cooling, as well as the repeated melting and solidification. Also involves some multi-scale, multi-physics phenomena. So of course, this kind of microstructure would have profound influence on the final product. So similar to the material design, we want to investigate the processing or the manufacturing process, its influence on the structural property as well as its structure. So we also need to build this scale framework. More specifically, we would like to have a melting pool model to predict the melt pool geometry and thermal profile at the microscopic scale. And this information will be fitted into this microstructure model to predict the evolving microstructure and defects statistics. And all this will be combined together to make an effective micro-continuum model. So of course, in building the materials model at disparate length scales, we need to consider the proper process parameters as well as multiphysics phenomena that could have influence on the evolving microstructure and the materials properties. So for example, for the microstructure model, we need to consider the laser power and its movement because that would affect the thermal history of this microstructure evolution. We also need to consider the possible multiphysics phenomena such as the recrystallization, solidification, melting, as well as phase transformation. So here shows our some results on the prediction of the melting pool, and we can see this melting pool geometry and its movement with the laser scan, as well as the temperature field. We can also have a very detailed picture of this melting pool from this prediction, consisting of only the fluid state, the mushroom zone, which is coexistent fluid-solid states, as well as the heat effective zone, where the phase transformation and the recrystallization could possibly happen. So here is another example, our combined phase field and thermal field to predict the microstructure evolution. This is during the solidification process and the polycrystalline growth. And here shows a final figure showing the grains as well as the grain boundaries. We only consider melting and solidification at this point. Further, we want to also add the phase transformation as well as the recrystallization to have a direct comparison with the experimental results. So we choose the phase field model because it could provide a very flexible framework. And so first we need to construct the free energy expression with contribution from the virus form of the free energy density. And then after we have this, then the evolution of the phase field can be predicted using the Allen-Kine equation, which is the gradient of the phase of the free energy. And this phase field can be easily coupled with other field analysis. For example, it can couple with the mechanical field analysis through this elastic term, and couple with the thermal field analysis through this chemical term, with their detailed free energy expressions are listed here. Also, we need a variety of material parameters to realize the successful and high fidelity prediction from the phase field model, where some of them can be obtained from the experimental database, and some of them we can characterize by ourselves. So besides developing the phase field and also the coupled field analysis, I also participate in some methodology development to realize the numerical technique to realize this phase field model. So we recently developed particle difference method, which in essence a mesh-free method